Good morning, everybody. I want to go through this Wave Basics worksheet with you and work out the problems, give you the answers, and see how you're understanding wave anatomy and wave behavior to start off this week. In problem 1, we have this fly that is sitting on a string, and this pulse is coming down the string. It's moving to the right, and so that string is the medium for this wave. The first thing it asks you to do is to label each pulse as a transverse or a longitudinal wave. So this type of wave that looks like a sine curve or a cosine curve, this is going to be the transverse pulse. This is how light moves, for example. Light is a transverse wave. This second example that looks like a slinky, you see this part here is pretty bunched up, this part here is stretched out. This is an example of a longitudinal wave. And sound is the one example of longitudinal waves that you're going to want to know. Sorry about the dog. The problem now asks us in part B to describe the motion of the fly when the pulse passes under it. So what you have to imagine is that this pulse is going to travel to the right. What's going to happen at this point when the pulse gets here? In other words, pretend that the fly is just going to hang on to the string. You're going to imagine that the fly would ride up and then ride down and then ride back up as this pulse passes this point over here where he's hanging on. And so the idea here is that with a transverse wave, the particle moves up and down, which is perpendicular to the motion of the wave. Right? So the wave's going to move to the right. The bug doesn't move to the right with the wave. The bug's going to go up and down because he's going to stay in the same spot. That's how transverse waves behave. Now let's try it with a longitudinal wave. The bug's hanging on to this part of the spring. This longitudinal wave is going to move to the right. So when this compression reaches the part where the fly is hanging on to, the fly is going to move to the left. And then when this compression part passes through, the bug's going to move to the right. So the idea here is to recognize that when this compression and rarefaction move through the point where the bug is, the bug's just going to move left and right with that longitudinal wave. And that's how longitudinal waves behave. The particles move parallel to the direction of the wave motion. Remember, that's different from transverse. With transverse waves, the particles move perpendicular to the direction of the wave motion. Now, in problem number 2, we have to indicate the wave type, and we want to show a wavelength. So you see this dotted line here for the transverse wave. That's like our equilibrium, our resting position. So this one's transverse, this one's longitudinal, same as in number 1. Wavelength can be defined with a number of points on these waves. I like to define wavelength as from one point on a wave to the same point on the adjacent wave. A lot of times students learn that it's from maybe crest to crest. This would be an example of one wavelength. But you could also define it from this trough here to this trough. That distance is also one wavelength, and that are the same distance. You can also pick any points along the wave itself, from this equilibrium position to this equilibrium position, for example. So as long as you have labeled from one point to another point and labeled it as a wavelength, you should be correct. So on the longitudinal wave, you have to identify the compression and rarefaction. So compression is a word you probably already know. Compressions are smooshed up parts. Here's a little bit of one on this left end, here's a little bit of one on this right end, and of course that's a compression in the middle there. Now rarefactions are the stretched out places. So there's a rarefaction, and there's a rarefaction. When you're comparing these two, a crest is similar to a compression. So in other words, on this transverse wave, the crest, there are these tip-top maximum displacement areas. A crest is corresponding to a compression on a longitudinal wave. And then, let's see what else. Oh, on the transverse wave, we have to identify the amplitude. So amplitude is from this resting line to a crest. From rest to crest is what I sometimes say. Amplitude could also be from rest to a trough. That just doesn't sound as cool as from rest to crest because it doesn't rhyme. But amplitude is the distance from the resting position to this maximum displacement on a transverse wave. Now we also want to identify a crest and a trough. I've already talked to you about those a little bit in this video, but the crest are the maximum positive displacements. The troughs are the maximum negative displacements. So that should be all the labeled parts for number 2. All right, let's flip over on the back. These are some pictures of sound waves from an oscilloscope. An oscilloscope just turns a sound wave, a sound, which is a longitudinal wave, into visually a transverse wave. It doesn't actually change the type of wave. The electronics in the oscilloscope just transfer the signal from a longitudinal wave to a visual transverse wave so that you can see it. So question number 1 says 2 of the sounds are low notes, 2 are high notes. Which are which? So when you talk about low notes and high notes, all the music students know this. The low notes and high notes are referring to the pitch of the sound. And in physics, pitch is related to the frequency. So when you look at the 4 choices for the oscilloscope, the 2 pictures that have low pitch or low frequency are letter A and letter C, because these waves are kind of stretched out. If you look at a wavelength, the wavelengths are pretty long, so that's low frequency. Long wavelength is low frequency. Then the 2 that have high notes or high frequency are the waves that occur more often, so they're going to have shorter wavelengths and higher frequencies. That's going to be choices B and D. They have shorter wavelengths, they occur more often, they are more frequent, so they have higher frequencies. So again, A and C are the low notes, and B and D are the high notes. Question number 2 tells you that 2 of the sounds are loud while 2 are quiet. Now, in terms of physics, the loud and the quiet has to do with the amount of energy that's transferred through the wave. So we're going to be looking at amplitude here. So the 2 sounds that are loud are the 2 that have the largest amplitude. So if you remember thinking about from rest to crest, letter C and letter D have the largest amplitudes of these 4 choices. So C and D are the loud sounds. That means A and B are the quiet sounds because they're shorter waves or shorter amplitude with that. That means there's less energy transmitted. So then the last question on this worksheet, question number 3, put it all together. Which sound is high and quiet? So you want a high frequency but a small amplitude. The sound that is quiet is going to be this one. Oh, wait, I'm sorry. No, that's loud. That's high and loud. This is high and quiet. It has small amplitude because it's quiet, but it's a high-pitched sound because it has a shorter wavelength than A and C. So letter B is the answer to question number 3. Alright, so what I want you to do right now is pause your video and then work on the next worksheet, which is the wave equation worksheet. I'm going to pause the video to switch out my worksheets, and when you're ready, hit play and I'll work through that one with you. Okay, now I've got the second worksheet for today. It's this springboard worksheet that starts you working on the wave equation. I'm just going to scoot this up a little bit so that we can go straight to the questions. You're actually going to start off without thinking about waves. We're just going to be thinking about sitting at a railroad crossing, watching the trains go by. It gives you a little bit of information. We know that each railroad car is 10 meters, and in 60 seconds you count 84 cars. So the first thing that it asks us to do is to write a ratio that represents the number of seconds it takes for each car to go by. So what I know is that in 60 seconds, 84 cars go by. So I could actually figure out the time it takes for one car to go by. Okay. Well, in letter B, it asks you to write another ratio, but this time you're going to be figuring out how many cars go by each second. That's a little bit different than what you did in letter A. In letter A, you know that 84 cars go by in 60 seconds, so we could figure out how many cars go by in 1 second. So when you look at those two ratios for question C, which one of those ratios better relates to the period of the train car passage? Well, I know the period is the time it takes for one car to pass. So I think the first ratio does that. The 60 over 84 is going to be a better representation of the time it takes for one car to pass by the crossing. And in question D, which ratio better relates to the frequency? Frequency is how many cars pass by each second. So I think the 84 over 60 is a better representation for that. So in question E, can we use that information and in thinking about the train cars with period and frequency to figure out the speed of the train? Okay, so if I know that 84 cars pass by the crossing in 60 seconds, and I know that each car is 10 meters long, I need cars to cancel out. So I'm going to set up a quick conversion here that one car is 10 meters. So that car unit cancels with that car unit, and you can multiply across 84 times 10, divide by 60, and you get 14. The units you're left with are meters over seconds, which is perfect. That's a speed or a velocity value. Okay, so we can calculate that this train goes 14 meters per second. Now let's start turning this into some physics and thinking about waves. If wavelength can be represented by the length of one rail car and t represents the number of seconds, write an equation for v, the speed of the train. Okay, so we used v was what we were figuring out. So the speed of the train is equal to the wavelength, which is the length of each car, times the number of seconds it takes for each car to go by. But that's not what this ratio is. We've got the reverse or the inverse of that. We've got 84 over 60, which was more like the frequency. So that seems like where we end up. But this question's asking us to put t in there instead. Well, we can do that. Go back up here and look really quick. Period was 60 over 84. Frequency was 84 over 60. So I think that frequency and period are just inverses of one another. So I can write that equation to give me the speed of the train with lambda for the wavelength on top and t for the period on the bottom. Now letter G is going to ask me to do what I already ended up with here. The speed of the train is the length of each car times this ratio, which was the frequency. So two big things come out of this. In part G, look down here at number 2. In part G, above is the wave equation. So V equals lambda F is the wave equation. It relates wavelength and frequency to the speed of a wave. Okay, but the other thing that you get from this work is to figure out that frequency and period are inverses of one another. So you can write frequency as 1 over period, or period is 1 over frequency. And those are important relationships because depending on what you're given in a question, you may need to use these different versions of this equation to solve. All right, so let's try some work down here. In number 2, we're given an ocean wave question. The ocean wave is 12 meters in length, and it hits a seawall with a frequency of 0.5 hertz. How fast do these waves move? So that's a velocity question. So here I think I can do V equals lambda F. I'm going to plug in the 12 meters for wavelength, and I'm going to plug in the 0.5 hertz for frequency. You can just multiply that out. The speed of these ocean waves is 6 meters per second. For letter B, we're working on sound waves, which is a longitudinal wave, but this equation doesn't distinguish between transverse and longitudinal waves. It works for any type of a wave. So I have the speed of a wave here. I know that because it's in meters per second, like a velocity would be. The tuning fork that's making the sound wave is vibrating 384 times each second. That is a tricky way of writing frequency. That's the hertz. 384 hertz is the measurement on this tuning fork. I need to find the wavelength, or lambda, in this problem. So I'm going to again use V equals lambda F. I'll plug in my 350 meters per second for velocity. I'm going to solve for wavelength if the frequency is 384 hertz. You want to isolate lambda, divide both sides by 384, and in your calculator you should get about 0.91 meters as your wavelength for this tuning fork. Alright, last one. This one's using light waves. The light waves from this laser pointer have a wavelength of 670 nanometers, and they're traveling at 300 megameters per second. What is the frequency of the oscillating source of these waves? So we're looking for frequency. Now, the only reason this problem is extra challenging is because you have a few conversions to do. Nano is times 10 to the minus 9th. So if you set up a little conversion factor here, 1 nanometer is 1 times 10 to the minus 9th meters. So that becomes 6.7 times 10 to the negative 7th meters. And then for the velocity, 300 megameters per second. The seconds is fine, but we need to convert this megameter to just plain old meters. So I'm going to put meter on top. I'm going to put megameter on the bottom so that it'll cancel out, like all conversion factors work. Mega is 1 times 10 to the 6th. So 1 times 10 to the 6th meters is 1 megameter. So that comes out to be 300 times 10 to the 6th, or 3 times 10 to the 8th meters per second. Okay, so that's a lot of conversions. I'm actually going to switch colors of my pens here so you can follow along. Now I'm ready to actually work the problem. I'm going to slide my paper over a little bit here. V equals lambda F. So we're going to use 3 times 10 to the 8th meters per second for the sound velocity. I'm going to plug in a wavelength of 6.7 times 10 to the negative 7th meters. And then the frequency is my unknown. So divide that in your calculator. Remember, if you are using scientific notation, when you divide and put this scientific notation number on the bottom of your calculator, you're going to need to put it in parentheses so your calculator follows order of operations correctly. And you're going to get a frequency of 4.5 times 10 to the negative 14 hertz. make sure you look on the right side of your calculator screen to get that exponent value. Now, for full disclosure, I just did this worksheet quickly, and this is the first take at the video, so if I have gotten something wrong here, let's make sure that we talk about it in the discussion board, or shoot me an email really quick. I think I did all my math correctly if I remember how to add and subtract exponents, but if I missed something, please let me know, and I hope that helps get you started for this week on waves. Have a great day, y'all.